Our final exam is on Tuesday of next week from 3:30 until 5:30 p.m. And we'll talk more about the characteristics of the test in just a minute. The last thing we're going to be covering today is in Chapter 16, Open Channel Design. We'll be talking a little bit about the procedure you go through in trying to decide how big a channel should be. So before we get into that, let's talk about the final exam. The exam has an emphasis on the material that we've gone over since Exam 2, but since the class is sort of naturally cumulative, I don't want to make any promises that you absolutely wouldn't see any questions from the earlier material. And in fact, I might have a few just very basic comprehension questions related to the older stuff. There were a number of question types that we didn't have a chance to assess on the earlier exams. When you only have 4 or 5 questions, but you did 8 or 9 procedures during a certain section of the course, then inherently you can't get to everything. But my intention is for the majority of the points to be related to the things since Exam 2. The exam will be slightly longer than the first 2 midterm exams. I went back and looked, and Exam 1 had 5 questions on it. Exam 2 had 4 questions, so I'm not going to make any promises about the number of questions because I might split them up into smaller bite-sized questions rather than larger high point value questions. But the main idea is that the exam will be a little bit longer, but you're going to have a lot more extra time because we'll be going from 75 minutes to 120 minutes. So if any of you felt like you were under time pressure for the midterm exams, I hope that the time pressure will be alleviated on the final exam. You should bring a computer with you, and the computer needs to have Excel because there will be at least one question related to the water surface profile stuff that we've been doing lately. You don't need to have access to water gems. We won't have any water gems questions, but because you're going to be asked to upload your Excel file at the end of the exam to MU Online, bring a computer that also has internet access so that you can upload the file that you create during the test. I'm going to talk about the equation sheet in just a minute, so you can have an equation sheet that you create in addition to the ones that I give you, but when it comes to the computer problems, you have to start with an empty spreadsheet. And I'll be circulating around the classroom trying to keep my eye on that people are starting from a blank workbook just so that everyone has the same advantage. So what that means is that on the equation sheet that you create, if you want to create like an outline of a procedure that will remind you what to do in Excel, then that might be a worthwhile use of the space that you're allocated. Or if you want to have a list of columns that should be in a certain formula, then I'd encourage you to do that. Now, that's not to say that it has to be the same exact way that I've showed you the solutions. And sometimes students think because I've given you so many template files that that's the only way to solve it. But in fact, that's not true. As long as you've got the equations, then you can kind of reason through what needs to be in that spreadsheet. So as long as you end up with the correct answer and you got there through the correct calculations, I don't necessarily care that you've got all of the same column titles that I usually use. Okay, so here's the stuff about the equation sheets. I'm going to print out the entire equation packet this time around, and let me bring up just to show you what the equation packet looks like and where you can find it in case you want to have an advanced look. The entire final page of the equation packet is related to the water surface profiles. And so it might be worth taking a look in advance to see what you've already got before you reinvent the wheel, because, let's see, equation sheet for exams. If you look at the final page, it's got the process equation for gradually varying the flow, rearranging Manning's equation for the slope of the energy grade line, and then the equations you'd need for each of the 3 methods that we've covered over the past weeks, the numerical integration, direct step, and standard step, along with a hint that, unfortunately, I guess I didn't emphasize enough in class, that when you've got supercritical conditions, that the formula is different for calculating the water surface Whereas, you know, if you're working in subcritical, you work from downstream to upstream, but for supercritical, you work from upstream to downstream, and so plus head loss instead becomes minus head loss. And I put that comment in when I was grading the homework that you'd submitted. A lot of people got the same depth for the, I guess it was the handout problem, around 2.5 meters, but that's not the correct depth. And the error was the people were adding the head loss when they should have subtracted it. So that's just an aside. The main point is that I think I've given you all of the formulas that you need, and so how can you wisely use the 2 pages of equations that you're given? You might want to define variables if you haven't already committed that to memory. Like I already mentioned before, you could re-emphasize in your mind what the solution procedures are for certain things, but the main idea is that you can have 2 pages, front and back is all right, and there can really be anything on there that you'd like. Isaac?
There shouldn't be more than one Excel file.
I'm not going to make that promise to you. No. I'm not going to box myself in on what the exam will or won't be because I haven't written it yet. So if I said something, I'd inevitably forget it, and then maybe I'd follow it by coincidence, and so, yeah. Any other questions about the final exam? So the question is, could the Excel questions be something from before? Like, for example, what?
I don't know. We have like
What, 3 reservoirs?
Yeah.
There won't be a 3 reservoirs problem. Yeah. All right. Well, so again, that exam is on Tuesday. So a week from now, we'll be done. I don't know if I'll have the grades posted a week from now. I'm going to try and do it as quickly as possible, but it'll be more lengthy than the other exams have been, and so I guess it all depends on how many questions you get right. Because if you get the right answer, it's really easy to grade these, but the more mistakes you make, the harder it takes to, the longer it takes to grade, and so anyways. All right, so just really quickly, I wanted to introduce a overview concept related to risk. Has anybody ever seen the movie with George Clooney? I think he's in Perfect Storm. You knew from the picture, right? All right, so what's the background of the Perfect Storm? Fill in the people who haven't seen it before.
Basically, he was out fishing.
Uh-huh.
The fishing got too good.
So we all agree they were fishing, though, right? We all agree they were fishing. And there was a storm. Yeah, all right, so they stayed out when they shouldn't have stayed out, and 3 storms converged in a single location simultaneously, and that's what was perfect about it. When they say the perfect storm, what they were really referring to is just how big and how bad could it potentially get. And it was a worst-case scenario of a very low probability that occurred. And so when we think about probability, it's a really important part of hydrology, and then by extension important part of engineering, because the flow rates that we design for are going to accommodate flows that happen maybe only occasionally. You know, in the last class period we talked about how you're designing a sewer to handle the flows when the city's all completely built out and some extreme condition like under really wet weather or a rare event. And so one of the ways to measure the probability of event is by annual exceedance. And that is a fractional representation of, on average, the likelihood of something being equaled or exceeded in a given year. Now the reciprocal, or the inverse of that, is return period. And return period is kind of how in hydrology we talk about storm sizes more often. You've probably heard the phrase the 100-year storm before. Now, a lot of people say that the storms that hit West Virginia last summer were larger than the 100-year storm. And so, on average, a 100-year storm has an annual exceedance probability of 1%. And so that means that, on average, in a given year, we should only have a 1% chance of the 100-year storm. So the equation that relates probability and return period and risk is this one that's shown on the screen. And just to illustrate that this is nonlinear, let's just do a quick, simple calculation of the risk related to experiencing a 200-year storm in a 50-year period. Because at first glance, if you didn't have this formula, you might think incorrectly that if it's a 200-year storm, there's a 25% chance that it'll happen in any 50-year period. But that ends up not being the case, as I think you'll see if you just quickly substitute the numbers in. Since our, here, the 200-year storm is what we're wanting to find the risk of, then in any 1 year, the probability of that is going to be 0.5%, or 0.005 is the P that we should use. So that means the P is 0.005, N is 50 years. That's the time horizon that we're considering the risk over. So the risk of experiencing a 200-year storm during any 50-year window is 22.2%. So it's less than the 25% that we might otherwise think. And one way to think about that is a 1-year storm, a storm that has the size that on average it comes around once a year. You know, there is some probability that in a given year you won't see the 1-year storm because it's only on average that it comes around once per year. You could have a relatively mild, dry year where you didn't see the 1-year storm. And so in this case, that probability is 22.2%. What's kind of interesting is if you consider the 200-year period, there's not even a 100% probability that over 200 years you'd see the 200-year storm. So if you said n equals 200 years, there's only a 63.3% chance that you'll experience a 200-year storm within a 200-year period. So if you do end up taking the hydrology class, there's more risk and probability there as we talk about the ways that you have to go through to calculate the flow rate that hydraulic designers will be sizing channels for. I mean, you don't have to wait even but a week to know for sure, right? All right. So what we're looking at today is channels to convey flow. And I've tried to give you a little bit of an idea of what would be in hydrology, that elective class for the fall. But, you know, all semester long we've just been given a flow rate Q that we're trying to evaluate what happens when you've got this certain amount of water going through a channel. But today we're going to be shifting gears and doing designing, where you're given a Q and rather than just assessing what is the depth, you're trying to say how wide or how deep the channel needs to be in order to convey the flow. Now the hydrology side of things is the calculations required to estimate what the flow rate's going to be for a certain storm. But today we're going to look at the difference between concrete lined channels like this. This is an irrigation canal that is man-made and very smooth, likely to lose less water due to infiltration down through the soil than a grass-lined channel. Now, of the two, this grass-lined channel obviously cost a lot less money to put in. And which one to go for depends on more factors than just what's your budget. It may be that sometimes we consider water as a waste and we want to promote infiltration. So if it's stormwater runoff, then we'd much rather have the water infiltrating into the soil than we would have it concentrating at some central location where then we have to build a pond or be concerned about flooding. But in this case, most likely what we're looking at is an irrigation canal where avoiding infiltration is really important because every drop of water that you lose to infiltration is a drop less that you have available to use downstream for watering plants. Somewhere in between, in terms of making a channel that's more scour resistant, would be to use riprap. And this is showing water coming out of a culvert, and then these broken up cobblestone rocks here. That's sometimes called riprap, and it's just to provide an armor to try and prevent the scour of the soil that's underneath that rock lining. And sometimes we even just will leave a channel as earth-lined, and the Ohio River is an example of a natural channel that is lined by earth, and the shape of an earth-lined channel is limited to the cohesive strength of the soil. And at the end of today's class, we're going to be talking about the angle of repose, that naturally soil has an angle of stability that it can make with itself related to the soil grain characteristics. And so it's an important thing that we have to consider the velocity of the water moving through an earth-lined channel and compare that to how strong and how cohesive the soil is to resist the shear force that's being applied. So there's a lot of factors that a hydraulic designer will juggle beyond just the economic cost of what lining to put in. It's sometimes infiltration is good, sometimes it's bad. We have to consider what's the velocity likely to be, and how concerned we'd need to be with scour of the material, and what is the slope of the ground. And a lot of the things that are important can't be changed, and slope is chief among those. You can't make a channel any steeper than it naturally is. You can actually make a channel less steep by meandering, but you can't make it steeper than the natural surrounding ground. Otherwise, the river or channel will keep getting deeper and deeper. Here's a picture of a canal in Florida. And if you've ever been down to Florida, you may have, as you're flying over, noticed that they have all sorts of drainage canals that are really a scar on the landscape. They're unsightly, but I guess it's better than living in a swamp. So they serve a purpose, that's for sure. The channel design has to match the intended use. And so that goes back to the idea of whether water is a resource or a waste, and whether you're trying to preserve it or if you'd be just as happy to have the water infiltrate into the ground. And also the expected velocities that you can see in the channel and how that relates to whether armoring has to be provided. So as engineers, we're always trying to optimize, and you remember that from the project, that you were trying to make the pipe sizes as small as possible. And in open channel, it's some of the same idea. We want to minimize the flow area. The reason why you want to minimize the flow area is that's what has to be excavated. You want to excavate as little material as possible, subject to other factors that also contribute to the cost. But remember, we've talked, I'm not going to use this marker today. They fooled me already. I brought my own. We've talked about that if you had a very shallow, wide channel, that there would be a lot of resistance. And so you may be able to get the same flow capacity with a deeper channel, but has a lower cross-sectional area, simply because in this sketch on the left, there's a lot more resistance along that wetted perimeter that's close to the flow area. Whereas the zones that are further away from the wetted perimeter aren't as inhibited by shear stress, and so that the flow conveys more quickly. So minimizing flow area is your most efficient way to convey a lot of Q without having to excavate a lot of fill. And excavation is one of the primary costs related to constructing a channel. It's not the only cost, though. So we can rearrange Manning's equation in terms of A. And if you want to have a small a on Manning's equation, then the way to do that is to have a low flow rate, but normally we can't control that directly. I mean, there are indirect ways to control the flow rate. If you think about a ditch that's conveying stormwater, you're going to have to convey more stormwater depending on what's built in the watershed. Like a, what's the development called where Target is in Barboursville? What's it station? The Merritt's Creek. Yeah, okay. So Merritt's Creek, think about, if you've ever been up there before, it's just acres and acres of roof and pavement. There's lots and lots of impervious area, where previously there was trees and leaves and vegetation and just a lot of things that were absorbing water and promoting infiltration into the ground. And so when they switched from the natural undisturbed land cover to a impervious surface, then that's going to greatly increase the amount of runoff there is during a storm. So that's an example of how you can indirectly adjust the flow rate that has to be accommodated. And here in Huntington, they've started to adopt stormwater ordinances that require new construction to trap water underground. And the new practice facility is an example of where they have some underground water storage under the parking lot. I think if you look at the parking lot at Cookout, they've got kind of like asphalt there that is pervious pavement. It's not real durable. It doesn't hold up well, but it does promote infiltration. So those are some ways to kind of shape upstream how much flow is going to have to be accommodated. But what we do have control over more directly than that is the N value, because that's related to the material of what's being used for construction. The wetted perimeter, remember, we want to minimize the wetted perimeter in order to minimize the cross-sectional area. And then the slope. You can't increase the slope, but you could, if you wanted, decrease the slope by having the stream go back and forth between 2 points. If you have a meandering stream, that increases the length. And so remember, slope is delta H over length. Delta H would be the elevation difference between 2 points. And so if you have a really long flow path, like is the case in a meandering stream, then that decreases the slope. So we want to minimize the flow area. Now, on the basis of shape, the best trapezoidal channel is one that looks like this. And here, the side slope, where 1 is the vertical and m is the horizontal component. You notice here, m of square root of 3 divided by 3 means that you're actually going to have a side slope that's steeper than a 1-to-1 ratio. So the best trapezoidal channel is really hard to achieve with an unlined material. Like you can't do it with sand or clay. You can do the best trapezoidal channel if you're using concrete material, or if you were blasting through rock, as occasionally happens. But you know, it's the best efficiency for a trapezoidal channel is a side slope that's kind of difficult to achieve because it's so steep. I want to point out one other note on this drawing, and that is freeboard. And we'll talk about channel design and how you have to calculate freeboard in a minute, but you would want to provide a little overhead, a little extra flow capacity in a trapezoidal channel, because you know, for one thing, you might have more flow than you originally expected, but then on top of that, this additional freeboard gives your channel capacity for any wind-driven waves. Like if you've got a windy day and it was all the way to the top, then the water could spill out of the channel simply because it's a windy day, or splashing, or you know, waves that are related to maybe a hydraulic jump upstream or downstream. So here are the geometric parameters for the best trapezoidal channel: wetted perimeter, the bottom width, the cross-sectional area, and the side slope. So we've talked about freeboard already. Now, the natural materials don't really allow a side slope this steep. And so because of the cost of putting in a concrete lining, you know, concrete lining would keep the soil in place, so you could have it that steep, but it's cheaper to just not use concrete and have a normal earth lining and make the channel a little bit wider. And so what we're saying is, if you made it a 1-to-2 slope, where 2 is the horizontal and 1 is the vertical, you're going to be excavating more area, sure, But the excavation costs of that additional area would be cheaper ultimately in most cases than lining the channel, unless you had some other reason to line the channel, like that water is so precious you want to prevent the infiltration. There can also be other factors that contribute to other economic factors that have to be considered, like sometimes there's not some place good to put the excess excavated soil. There's no place to get rid of it, or if the real estate is particularly expensive. A trapezoidal channel that has 1 to 2 side slopes is going to be much wider than the channel that's shown here. And so if you're in a high value neighborhood where paying for the excess right-of-way is going to be prohibitively expensive, then that's another case where maybe it would just be cheaper to line the channel with concrete rather than paying for the extra channel width. So we've talked about the trapezoidal best shape. The most hydraulically efficient rectangular channel is one that's a half square. Most hydraulically efficient triangle is also a half square, but it's turned on its edge, so it would look like a half square like this. So the triangular, we wouldn't see the top at all. All right. There's 2 channel slopes that we have to distinguish between. And one is the longitudinal slopes. That's the slope that the water is flowing in that direction. If you have a really shallow slope, then the water is going to move with a low velocity. It will give greater depths. And one of the things that we have to be checking on is minimum velocity. Why was minimum velocity important in sewers? Sediment buildup. So the same thing is going to be something we check on here in open channels. Are particles settling down to the bottom of the channel? But there's an additional concern as well. In sewers, since there's no light underground, we don't have to worry about weeds growing. But in an open channel, there is the possibility that a really slow-moving water would allow unwanted plants to begin to grow. And then there's a whole lot of maintenance that goes into mowing the grass that can grow in the channel and keeping cattails at bay, and especially in water bodies that have lots of nutrients in it, like nitrogen and phosphorus, then the vegetative growth can really get out of control. So we're going to do a minimum velocity check to see if it meets some threshold to prevent sedimentation and vegetation. Really steep slopes, though, which are going to avoid sedimentation and avoid vegetative growth, they can scour the material depending on what it is. So we have maximum velocity constraints as well. So here are some like typical side slopes. Now those were all about longitudinal slopes. The side slopes that we're talking about are these ones, the side slopes. You can't, the longitudinal slope is in the direction of flow, so into the page, but the side slopes are governed by the material. And so here are some side slopes that can be achieved with different types of earth. So for a loose sandy earth, for instance, you could have 2 horizontal to 1 vertical, and it would be kind of like a sustainable shape. In the case of rock, it could be nearly vertical. You could have a rectangular channel if you wanted to chisel into the rock, and if it's stable, without fractures in it, and all the shapes in between. Freeboard that we've talked about, that excess capacity at the top of the channel, also is useful when a channel has to go around a bend. Because just like when you go around a bend in your car and everyone sort of goes to the outside edge, the opposite direction of the acceleration, you remember in fluid mechanics we talked about when a tank of water is accelerated to the right, then the water will increase on the left. So if you have water going around a curve, the water levels can increase in one direction and decrease in the other. So freeboard is also useful because superelevation occurs. Let me show you. Superelevation, see this new water surface here, the blue line. This would be if we had a curve that was going around towards the right. then the water level would increase to the left, decrease to the right, and the overall distance of the superelevation can be calculated according to this formula. H sub s would be the total difference in elevation between the left side and the right side. So it's calculated by the velocity squared times the top width of the channel divided by gravitational constant and then the radius of curvature from the center line of the channel out to what the channel is curving around, if it's following kind of like a circular curve. Now, freeboard is usually calculated just with kind of an empirical rule of thumb, 0.55 times the square root of c times y. And c is, I don't know, kind of like a meaningless coefficient that just has been developed over observation, and we can linearly interpolate between a low flow rate condition where you need relatively less freeboard and bigger channels. We'd say you need a little more freeboard. And so in an example we're going to be working in a moment, what we'll do is we'll linearly interpolate the c value. And the way to do that is, if we look at it graphically, it's the c value is going to be on the vertical axis. So it varies from 1.5 to 2.5. And then on the horizontal axis would be the flow rate, where at the lower end it's 0.57 cubic meters per second. And then up the upper scale it is 85 cubic meters per second. And so you just linearly interpolate between the two. And so the slope of this line, the delta c divided by delta q, would be that says 2.3, it should be 2.5. Okay, so 2.5 minus 1.5. And then the delta q, 85 minus 0.57. And so when you get the slope of this line, you would multiply that slope by however much extra capacity above 0.57 cubic meters per second you're carrying, and then add it to 1.5. So just standard linear interpolation. C is going to be 1.5 plus some amount, something minus 1. It will be the actual flow rate that you're seeing minus 0.57 multiplied by the slope of the line. So we'll get to that in a minute. But what you need to check at the end is making sure that the freeboard that you've established, that extra height above where the water surface is expected to be, you need to make sure that at least the freeboard is greater than the expected superelevation height. Now, line channels are nice because it allows you to get away with increased velocities, decreasing seepage, and they last longer. It's less likely to have the channel threatening homes that are near the stream banks. And just right across from my house where I live, my neighbor has a really nice garage, and in the years since I've lived in that location, the stream has basically scoured away about half the distance between the stream and his garage. Every year the channel is getting closer and closer to his garage, and he knows it. He's planning to try and put in some concrete lining, and he doesn't want his garage to fall into the river. And so if only the channel could be lined, then he wouldn't have that problem. The procedure for designing a lined channel is to check and see what material you have available to define the end value in the second step, and identify the flow rate to be carried. And that's not always a simple process, because all hydraulic systems are going to eventually fail. It's just a matter of how frequently do you want them to fail. In other words, if you're putting a culvert in someplace at the bottom of your driveway, for example, there's eventually going to be a storm that is too big to be accommodated by the capacity of that culvert. It's just how often do you want the water to be flowing over the culvert instead of through it? Can you tolerate that culvert failing every 5 years, every 10 years? Now sometimes the design storm is specified by like a federal statute. In the case of interstates, the hydraulic systems that are associated with interstate freeways are supposed to be big enough that they can handle the 100-year storm. But not all municipal not all municipal drainage networks are that robust, because I guess the stakes aren't as high. In the case of an interstate, people are driving 70 miles an hour, so if there's a lot of water coming in to the travel lanes, then people are going to have a much more serious accident than, people sometimes drive 70 miles an hour on 3rd Avenue here, but they shouldn't be in theory. So it would be less risky if the water's getting into the travel lanes here. So anyways, identifying the flow rate to be carried, in the case of today's example, that'll just be given to you directly, but in other cases that's both a hydrology question and a regulation question of how much water do we have to get out of the system that's going to be drained. We'll be calculating the normal depth with Manning's equation and then checking velocity for requirements related to vegetative growth and sedimentation. All right, so here's the example that we're going to work. This is a channel that we've decided on reinforced concrete where we expect the N value to be 0.015. We want to be the best trapezoidal channel, meaning it should have that side slope that is a little bit steeper than 1-to-1 ratio. And so in the best trapezoidal channel, here are the characteristics: the cross-sectional area, wetted perimeter, trapezoid, and so on, as a function of depth. Okay, so the slope is given, and then we're going to have to check on the superelevation height at the end. And so the turn radius here is given as 5 meters. So you'll use that as the RC, the radius of curvature, when we solve this channel. So the steps are numbered. We want to find out how deep the water is going to be. We're going to find out what's the velocity like at this design condition. And then also make sure that whatever freeboard above and beyond the flow depth we pick is large enough for the superelevation height. All right, so calculating the C value is really just kind of a preliminary thing. Up till now we haven't done any real hydraulic calculations. We just said, well, it's concrete, so N is 0.015. We're finding the C value that we're going to use later on. But when it comes to finding the normal depth, you have to say, all right, well, we're going for the best. And so the best, the cross-sectional area is 1.73 times whatever the depth is squared. And then the wetted perimeter is 3.46 times y, which is whatever the flow depth is. So you're going to substitute that into Manning's equation for A and for P. And so everything will be known. The Q will be known, N, slope. The only unknown at that point will be the depth, y, and you need to solve for the depth once you substitute those things into Manning's equation. So get to that point, and I'm curious to know what depth you get. Hopefully it matches the one that I calculated earlier. All right, so we got the normal depth, 0.751 meters. And since we're trying to find the velocity, you can use that normal depth to find the area with these. So having the cross-sectional area calculated will allow us to find the velocity. It should be about 2.46 meters per second. And then we check that to the criteria, 2.46. Where does that put things? Well, for one thing, if we had a non-reinforced lining, we'd be in trouble because that's a relatively high velocity. So it's a good thing that this is reinforced concrete because otherwise we'd be exceeding that limit of 2.1. But it's high enough that we should expect that the sediment, whatever sediment's in the water, is going to continue to be entrained. It's moving along at a fast enough velocity that the particles won't settle. So the mixing is going to keep all those particles suspended. And also, it's moving fast enough that it pushes plants over, that they can't really establish a good root zone. So it's going to prevent vegetative growth, although won't, I guess limit would be more realistic. It's not going to prevent it because plants will find a way to grow, but they're not going to grow as well as they would if the velocity was slower. So things are looking good for the velocity. The last thing, calculate the freeboard and then see where things are at with the superelevation. Okay, so the freeboard, we want to, the depth of flow is going to be 0.751 meters, and then on top of that vertical height, there should be an additional 0.588 meters of additional elevation that is for the wind-driven waves and the superelevation and a little extra capacity and so on, splashing. The superelevation, if you calculate that, is 0.214 meters. And just to go back to the drawing of what that means, that is, it's going to go up on one side and down on the other. So it's not that it's going up just in one, it's not going up the full amount, it's only going up half the amount, because here you can see from the sketch of the superelevation that if it's going up on one side, it has to come down on the other. And so the superelevation measures the overall distance, vertical distance between those two extremes. So we'll have plenty of freeboard. You'd really have to have fast-moving water, high velocity, and a narrow radius of curvature in order to have superelevation that gets more than the freeboard. Any questions that you wanted to ask about? Should I switch back to the solution one more time? Any questions on this? Okay, that's channel design. Things are a little bit different when it comes to unlined channels because we have to worry about the cohesive strength of the material that the channel is being built on. And so the way that we do that is calculate the shear stress on the bottom of the channel, and we've seen this formula before where it's a function of the slope of the energy grade line. If we have uniform flow, then the slope of the energy grade line is parallel to the slope of the channel, which is parallel to the water slope. And so we can just put in whatever the downhill slope is and calculate the shear stress. The shear stress on the sides of the channel are going to be a little bit different depending on the angle that the channel sides are built at. And so you'd use the contact angle to calculate the side shear stress. Now here's a good diagram that shows the angle of repose. If you've ever seen sand being piled up maybe from a conveyor, you'll know that it forms kind of a natural angle, and it can't be steeper than that simply because of the material properties. The angularity of the sand has a function. The moisture content has a function as well. But here is some typical angles of repose for different particle sizes and how angular and jagged the particles are. The more angular they are, and if the particles are round, then they tend to roll off of each other, and so there's a lower angle of repose, as compared to angular, misshapen, non-spherical particles that kind of interlock and lead to a higher angle of repose. So we have to bring in the geotechnical engineer to describe the soil characteristics when we're doing an unlined channel design. And besides that, though, the procedures are largely the same, where you're trying to minimize the excavation area because that can contribute to cost. You're concerned about the potential for scour, but then at the other extreme, low velocities, you're also concerned about sedimentation and plants growing. And this time the plants are going to grow better than in a lined channel, because for a lined channel they'll usually only grow in seams in the concrete. But in an unlined channel they can grow all over the banks. And there are little boats that are designed simply to mow vegetation that grows in channels. And this is pretty common in Louisiana, where the water is moving very slowly in some of the backwater areas that have very shallow slopes, and so there's heavy nutrient loading there, and the plants grow prolifically, and so barges have to go through these channels that are supposed to be navigable. Barges will have to go and mow down the weeds several times during a season. So again, the velocity can give us an idea of how well vegetation is going to grow. So channels are sometimes built in grassy areas. Rather than having an unlined channel just like strict soil, one of the ways to prevent scour is to put a grass lining. And then the other advantage of having a grass lining is that it also can help to promote infiltration if the water is kind of considered waste. And so along the side of roads, oftentimes in channels that are meant to convey stormwater, they'll have grass grow. And what I'm showing you right now is a table of retardance class. And this retardance class is related to the resistance that these grasses provide for water that's flowing along it. And so the retardance class, if you know which species of grass you have, and then product of velocity and the hydraulic radius, then the Manning's N can be looked up off of a table like this. And so what's important for you to understand is that Manning's N value is variable for grasses. And so as the velocity times the hydraulic radius goes up, the N value goes down. So let me do a little sketch of grass to illustrate what's happening here. Here's a normal channel, and let's say we've got a grass-lined channel. All right. Those lines represent grass. All right? I think you get the point. That's nice, right? So the water is going this way. Why is it that increasing velocity, do you suppose, decreases the N value? It pushes the grass over. Exactly. So when we talk about roughness elements earlier in the semester, we'd say that if you've got whatever it is, it can be steel, it can be concrete. We talked about equivalent sand diameter. If it's projecting into the flow field, then there's a higher amount of resistance. Well, as the grass gets pushed over, then the N value decreases. And so the first thing you do is you'd look at the retardance class, and so things that have a high level of resistance, these the A-class plants, weeping love grass, I don't even know what that is. But I've heard of kudzu before. We've got kudzu in West Virginia, and a lot of it grows if you go out on the way towards Fayetteville. You see loads of it. Lots of resistance, kudzu. Bermuda, on the other hand, not a lot of resistance there. Burned stubble, Bermuda grass, that sounds like my lawn. The burned stubble part, anyway.
What's the difference in between the two weeping love grass? One doesn't have a space in between.
And then down here, it's if this is an excellent stand, meaning it's in good condition, versus like, do you have patches of bare soil? So excellent stand versus good stand, unmowed, so it's not just the space. Yeah. It may. All right. So these grass-lined channels are desirable because it helps to prevent scour that would otherwise occur if it was just bare soil, promotes infiltration, and it's aesthetically pleasing. It's nice to drive along a road that has a grassy ditch compared to if it's just a ditch with dirt in it. But then on the disadvantage is that the grass has to be mowed. Otherwise, it's going to reduce the flow capacity of the channel. If you have a lot of weeds projecting into the into the channel, that's going to increase the end value, decrease the flow area. So it's all about maintenance in a lot of cases. We're getting awfully close. This is the last slide of the semester here. I wish I could say we're ending with a bang, but this is kind of just a pedestrian table of suggested maximum velocities depending on what the material is. So let's really draw this out. We've got another 6 minutes to spend on this slide. If you've got rock, the water can flow 20 feet per second over rock. That's good. Good rock. So we're talking like your AC/DC, Leonard Skinner. Okay. Poor rock is, poor rock, what would that be? Boston. No, actually I like Boston. I don't know why I said that. No, Van Halen would be poor rock. Literally, right? Yeah, yeah. Now you'll remember the term, right? So maximum velocity is a function of the material that you use for obvious reasons, because sand is going to be washed away more easily than clays will. Clays are cohesive. And then different types of grass can resist different velocities. You know, we said that above 2.4 it should be reinforced lining, and here's a little bit finer look at that. If you have, I guess there's a type of grass called smooth brome. So 1.5 meters per second will be erosion resistant soil level. So anyways, end course, get out. No. No. All right, so I'll see you on Tuesday for the final exam, 3:30 to 5. It's been a pleasure. Take care.